later, yeah. So I throw with the velocity upward like this, and let's say V0 is 100 meters per second. Now it's looping up, right? It comes back down, and on the way down, it's about to hit the ground. Well, the velocity at the end has to be something less than, not less than or equal to, just less than 100. I know that because I was told that in the beginning, I throw the object with the speed greater than terminal speed. So on the way down, what might the terminal speed be? 80, 90, 70, but something less than what I threw it with. Okay, that's, God bless you. That's what the first sentence states right there. So I know that on the way down, it's going to land with a speed that's something less than 100. So if I want to know when it has the most air resistance, well, drag force is proportional to either V or V squared. These are the two formulas we wrote down. Well, either way, the higher the velocity, the higher the drag force. So since the velocity was greatest in the very beginning, and it will never get back up to that velocity, it has to be just after it was thrown that it has the most air resistance. Okay, it's not about like direction up or down. Not about like, ooh, gravity's against me with me. Remember, drag force or air resistance is a function of velocity. It's a function of velocity. And that's what the test is going to primarily look at. They're not going to really be going into detail about that lump parameter 1/2 CA rho. Remember that whole thing? That's not really going to be the concern. It's going to be that you understand that the higher speed, the higher drag force. That's the key here.
So all of the things we learned in shear physics pretty much were like it lands at the same speed at the end of the parabola.
Well, that would be fine, Matt, if the problem said that there's no air resistance. But this clearly talks about air resistance.
Yeah,
so you have to drop that out of your head. When it says that, yeah. If it said no air resistance, then yeah.
It's stuck in my head that it's like,
I understand, for sure. I'm teaching that right now in physics, in honors physics, and I say it all the time. But I always say, like, without air resistance, this is true. Without air, in an ideal situation, this is true. But it's not when you look at air resistance, yeah. 4 is very similar to 3. A ball of mass m is thrown downward from the edge of the curve with an initial speed that is 3 times the terminal speed. So again, what's happening? You're throwing it down with a speed faster than it can actually achieve on its own. So what's happening as it goes down? It's going to start to slow down. The object has to slow down. I throw it with a velocity of, say, 90 miles per hour downward, but the terminal speed is only 50 miles an hour. Well, that means air resistance is going to suddenly slow this thing down right off the bat. So it has to be slowing down. So initially, the drag force is upward and greater than your weight. The only way to slow down is to have a negative acceleration, and that means that the upward drag force has to exceed the weight pulling down. So when I think of, I know, it's a bit tough, right? So here, let me give you a diagram. Here's the object. You're on a cliff. It's thrown downward with a velocity initially of, say, 100 meters per second. We know that that is 3 times the terminal speed. So as it starts to fall, it's going to reach terminal velocity, which is only going to be 33.3 meters per second. What's the only way an object can go from a faster velocity or speed in this case, to a smaller speed? It has to decelerate, which means that the net force on this object has to act opposite motion. And if that's the net force, that means that, hey, it's got 2 forces acting on it. It's got the drag force and it's got its weight. Drag force must exceed the weight in order for you to get a net force acting upward. This needs to be greater than this so that you have a net force acting upward, so that acceleration acts upward, and therefore your velocity, which is acting downward, reduces. Remember, the only time you're going to slow down is when your velocity and acceleration are opposite in direction. You can't slow down unless you're linear motion. You can't slow down unless your velocity and acceleration are in different directions. So this object is moving down toward the Earth. The acceleration must be upward for it to slow down. Which is what it's doing here. A very similar question to the last one, asked differently. Asked in the sense of free body diagrams here, right? Notice the need of a free body diagram, whether it's mentally or writing it out. Whereas the previous problem, you didn't really need a free body diagram. The idea behind the last one was a little bit different, right? This was the idea of kb squared. This is saying, hey, drag force and weight are not always going to be balanced. If you're going faster than you should be, it means you're going to have more drag force. Eventually, though, when you get to this point, what's the free body diagram going to look like here? Very good. It's going to be an equilibrium because this is terminal velocity. It is a terminal velocity once reached will not change. I'm falling 3 meters per second, 4 meters per second, 5 meters per second. And say 5 is my terminal velocity, the rest of the way down, I'm going to be at 5 meters per second the whole way. So from this point on, we're in a state of equilibrium for forces. Here, we were not. Here, the upward force far exceeded the downward force.
So when I did it, I was thinking that there would be a change in acceleration. Does that ever play a role in that?
Would there be a change in acceleration? It would actually, Max. The entire way down, there would be a change in acceleration. As 100 gets closer to 33.3, the acceleration felt will be less because this vector is going to get shorter. Think about this. This is a great question he's asking. It didn't affect the answer, but the idea is right. Fd is the drag force. As the velocity gets less and less and less, closer to 33.3, Fd as a vector gets shorter, doesn't it? This drag force is what we say. Drag force is proportional to kV, or kV squared, right? So as a result, if we have less velocity, we'll have less drag force. So later on in the problem, the deceleration is less. So maybe the deceleration in the beginning is like -10 meters per second squared. Then maybe toward the end it's -2 meters per second squared. Until finally we're in equilibrium, and then the deceleration is 0. So the deceleration absolutely changes. Yes, it does. But it doesn't affect my choices. Okay? But good analysis there, Max. That's very true. How about what is this, 5? I don't remember. Number 5. 4 people. So how about 5? Anybody want me to go over 4 of you that had trouble with this? So I'm happy to go over it. Yeah? Okay. An object moving in a circle at a constant speed. Okay. So why can we rule out the other choices is really the question here. The answer is D for sure, but why can we rule out the other one? So Matt, tell me why A isn't it. Or give me a reason why one of them isn't it. Go ahead.
Well, I was going to say for E, it's not B because there's tangent to the circle. It's not accelerating outward. The acceleration's always perfect.
So what's tangent to the circle? What word would have to replace that statement there?
Velocity.
Velocity. Very good. So this is incorrect. That's why, because it says acceleration. If it said velocity, that would be true. Another one. Go ahead.
For A, that one says only one force. So if you could have one force inducing acceleration, but you have two forces.
Yeah, the big problem, right? The big term. It had what? Friction and the normal force component, both giving it a radial force component inward. Remember, on the bank turn, the normal force pushed in, and so did friction. You can absolutely have multiple forces provided. Remember, multiple forces provide what we call FC. Multiple forces can at any given moment. It could also be one. It could definitely be one. How about B or C? Why are those out? Chip?
B isn't correct because any object moving in a circle has to be accelerated.
Because it's changing its?
Velocity.
Because it's changing its?
Direction.
Very good. Velocity is changing because the direction is changing. So when that happens, you have to have acceleration. So it is accelerating in this case. And how about C? How about the last one? What's the key thing here? Yeah, go ahead, Chip, again.
It's not an actual force, it's more of a feeling, so.
Yeah, this is not correct. If we're going to use a word there, what word should have been there? Centripetal, not centrifugal. Centrifugal effect is the desire to move outward. Okay, keep that in mind. Okay, so we got D. And D makes sense. It has an acceleration of constant magnitude. What is not constant about the acceleration? The direction. The direction of acceleration, although always toward the center of the circle in our minds, changes because the center of the circle changes with respect to where the object is around the circle. If it's at the top, then it's inward, meaning down. If the object's at the bottom, then it's inward, meaning up. Right, left, right. Okay, keep that in mind. Good question there. How about 6? 6, 3 people got wrong. How about 6? Anybody want me to go for 6? Yep. A 0.2 kilogram stone is attached to a string and swung in a circle of a radius of 0.6 meters on a horizontal and frictionless surface.
I just had trouble finding T.
Okay.
2.5.
Okay, yeah. So the revolutions per minute part? Okay, so we have 150 revolutions per minute. We want to know how long it takes to make 1 revolution in terms of seconds. We want a time period in terms of seconds, really. So when I look at this, I start the problem by saying I've got 150 revolutions per minute. I got to convert this right away. So I'm going to multiply this by, in this case, 1 minute. This is why I should put units first and then put numbers in. 1 minute per 60 seconds. So 150 over 60 is going to give me 2.5. So 2.5 revolutions per second is not a time period, though. How do we figure out the time period of revolution?
Well, you have revolutions, so you have to find the circumference of the circle if you want revolutions. So you get 2 pi times 0.6. So
Where's the 0.6 coming from?
the radius.
So 2 pi times r is going to give us the circumference. Over time, this will give us the velocity or the tangential velocity.
And then,
So what's the time is the question, Spence.
you don't do you need time?
I think you need the time for this.
No, I mean, the time would be 1 second, but what you do is you have 3.77 meters for the circumference.
You can multiply that by 2.5. Yeah, that's how many revolutions you have per 1 second.
Okay. I would also just, let me point something out. I like what you're saying for sure. But it might be easier just to say to yourself, if it's 2.5 revolutions per second, how many seconds is it per revolution? Right? We know we can invert things, and if we invert something, the units also invert. So if I wanted to figure out, because the way I taught it the other day in class, if you remember, was you could figure out the time period and plug t in where it's circled in red. You know the radius, and that'll give you v. So I saw this as 2.5 revolutions per second and thought, oh, that means it's 1 second for every 2.5 revolutions. So this number, as a fraction, turns out to be our decimal 0.4. So it's 0.4 seconds, 0.4 seconds per revolution. And we wanted to know the time for every revolution. So that's going to go back in up here. See what I'm saying, the difference there? It works either way, obviously, right? When you look at the math behind it. So we've got 2 pi times the radius, 0.6, over a time period of 0.4. This will give us v. And then we want to know the tension force. So tension is the only thing giving this circular motion. So we know that tension equals mv squared over r. So as a result, we can plug in the values we know. We know m is 0.2. V is that number from above. Whatever this turns out to be here in yellow, that goes in for v, and that's going to be squared over the radius, which is 0.6 meters. Okay, that would give me my final answer to this. Yeah, I see what you're saying. So if you have 2 pi r as circumference and you multiply by 2.5 revolutions per second.
Because 1 revolution is 2 pi r.
Yeah, because it's the same as dividing by 0.4, right?
This is the same, you're just flipping over.
And you're using, in that case, you're getting the velocity, right? So you're using, to do that, Spence, what formula are you using? Or are you just balancing units?
I did the same formula. Because 2.5 revolutions a second is still a velocity. I just substituted for revolutions.
And what about this formula here? Do you remember that formula from last year? V equals R omega.
Omega, and that'd be the...
But omega has to be in radians per second. So this would work as 0.6 times 2.5 revolutions per second times 2 pi radians per revolution. So that's why the math you said works. You see what I'm saying? So you end up getting, you did 2 pi r and then you multiply by 2.5. That's this right here. 2 pi times r times 2.5. So whether you realize it or not, that's the formula you end up using. But you can always convert by balancing units. Okay? It doesn't matter either way you solve this, but the idea is that you need to figure out what the velocity is. So I found the time first and then found the velocity. Spence said, hey, we've got the angular velocity, omega, multiplied by r to get v. How about number 7? Number 7. Number 8. Number 8, why is it 4 real quick? Because that's an easy one.
It's v squared.
It's v squared. Remember, F equals mv squared over r. So if v doubles, the force has to go up by a factor of 4. 9. Everyone got 9 right in the whole class. Awesome. It's the only one everyone got right. Out of all of them. Yeah, one people got right or wrong. Very good. And you know what's interesting, actually? I thought 9 was going to present issues because of the 25G. I was waiting for someone to say, how do I use 25 grams here? Think of that as mass.
That's
Did a lot of people do that at first?
Yeah.
That's okay. I'm glad you recognize that afterwards, saying like, wait, G is not about grams. And recognize also there's no space. You see the typing here? 25G. So it means 25 times 9.81, or 9.8 is what they're saying. So if you're talking about units, there's always going to be a space. So that's a good indicating factor that it wasn't about grams. And would you be able to solve this actually?
Yeah, I knew it was wrong because like it would have been 5 if it was just 25 for B, and like that wasn't one of the answers. So.
Well, I agree with that, but I'm saying though, I think a couple people initially might have thought of 25 grams as a mass.
No, oh yeah.
And I'm like, how would you get an answer then, right? You would have a radius, you would have a mass, and you'd be trying to find AC. AC doesn't even have mass in it. It's V squared over R. So that would be also the way to recognize it, not including
No,
mass.
so would it be like it could just not be moving at all? Like if it's just saying that it's 1 meter from the center and then it weighs 25 grams, then that's it. Like, so it's not saying it has an acceleration.
True, because they're not giving you an acceleration, so how would you be able to calculate the speed in the first place? Yeah, you have to recognize that you need A in this problem. 10, a lot of people have struggled with, so let's go for 10.
I thought it was like a trick question.
Yeah, so let's discuss what happens here. First, the centrifugal effect is mv squared over r, right? That's really what it is. The centrifugal effect, the desire to move outward, is mv squared over r. So the question is, does the desire to move outward exceed the desire to pull inward, which is caused by, in this case, friction? You're given the friction force, so you have that number. So an object moves in a circle, it's going to look like this, and the frictional force is 900 newtons already. Well, what's the desire to move outward equal to in this case? 1,000. It's 1,000 mv squared over r. It's 1,000 times 10 squared over the radius of 100. These cancel, giving you simply 1,000. So when you do sum of the forces equals mv squared over r, this side is 1,000, and this side is only 900. So the friction force is 900. The desire to move outward is 1,000. So the desire to move outward wins the battle. You see what I'm talking about here? That was the fastest period. It's only 50-minute periods, yeah. Listen real quick. So this last one makes sense first? Okay, second, here. I want to quickly, before you guys walk out the door, I know you got a class, I wanted to show you the upcoming schedule for what you can expect after break. I'll send this as a quick email so you can see it. Okay, but this is the schedule after break right here, what we're going to be doing. So we are this column right here. So we're going to come back on Monday and do a circular motion lab. The lab is already on Moodle. I want you to read it over break. Is that clear? I want you to read the whole lab over break. It's a little bit confusing. It took me like at least an hour to understand it myself last night. So I really want you to read through it carefully. Okay, I know, I'm saying it's going to take a little while. And it was just because I was reading it improperly. So be careful when you read it. I'm going to give you free response quiz on circular motion. We'll do some more 6-3 problems just to practice. You'll have your test on 6-1, 2, and 3. Remember, I'm repeating 6-1. So go back and think about that. It's not just 6, 2, and 3 in the test. And then I'm going to give you like a mid-year practice AP on this day. We have class 5th period this day. The test will be an hour and a half, so you can expect to spend another 27 minutes after school that day. I'm telling you now, there's no other way for me to do it. And I'm not going to split up into 2 days that are one's 63 minutes and one's 27. So this day is the last one. Okay, and then this is the end of the quarter right here. This will not count in your quarter grade. Okay, this will be the last grade for your quarter grade. I'm not going to count a practice AP exam just because I want you guys to take it without any nervousness for this one. We will do a couple more of these as the year goes on, and I might start counting as grades once I figure out an appropriate scale. It's the first time teaching this, so I have to think about scoring and scales for these kind of tests, okay? I'll send this to you over break, but please read through the lab over break, and I might also send you some practice for response on anything from the year, just to look at over break. Don't do like all of them in one day. Maybe take one day, another practice for another day. Consider that, please, okay? Thanks for waiting, guys. Thank you for break. For those who missed class, I'm going to have Brad. I know you guys who were out. Sorry about that. Those who missed class, that's all right. Check next door, that's where we go. I'll check the bottom drawer in this area where we have all the extra copies. If we do, I'll email you right away. Okay? Yes, Matt, so feel better?
Yeah, I just need some water. So yeah, it's like one of those like really long things.
You seem like you're about to like yak.
Yeah.
So I'm like, go.
I felt it. But for tomorrow morning, 4th period, I think you have free. Could I meet with with you like 20 minutes?
Sure.
Yeah, I've been getting the right answers on the homeworks, but the way I'm approaching them is a little bit different from what
Okay.
I've been seeing on Slater when I check it.
Okay.
So I just want to make sure I'm getting the right thing.
Yeah, 4th tomorrow?
Yeah, no, first tomorrow.
First tomorrow.
Yeah,
Got it.
Tuesday, first.
Okay, sounds good. Ah, thanks, Chip.
You think you could
I
maybe
do.
consider giving us like a graded assignment over break, or like an extra credit something to do over break? Just boost our grade.
I guess I could. I mean, I'm going to give you guys already a bunch of practice for response problems. So I could just count those as a grade. I mean, the thing is right now, Matt, to give you a grade that would really help your average or your grade would probably have to be like a quiz or a test in that category. So what I give you a grade is going to be like homework. Your homework category is already probably topped out of homework grade. You know what I mean? So unless I give you guys a take-home quiz, or unless I call that a take-home quiz, but if I do that, then I get nervous that people are going to be like freaking out about getting every single exact thing right. And like, let me think about it, Matt, to be honest. I'm really not sure how to answer that right now, you know? Yeah, I'm just trying to think about even if I did it, I don't think it's going to help your grade if I count it as homework.
My homework's already 100.
That's what I mean. And your labs are pretty good right now. You guys turned in a recent lab to me, the inclined plane. The terminal velocity you're all just getting credit for, which is easy. That's a nice grade.
Yeah.
And then the one that we're going to start next week on circular motion probably won't count until the third quarter. It's a grade. You have 9 labs for this semester so far. So I'd have to count it as a take-home quiz technically if I gave you guys a grade for response. Let me think about it.
Okay.
I'll decide. Let me look at everybody's grade overall in the quarter too.
Okay.
Okay. All right. You feeling you all right? You were away for swimming.
Yeah,
Everything good now?
yeah, good. I actually felt that like the questions I had wrong was like kind of like stupid, but I think so. I feel pretty
You
confident.
saw the videos up for the 2
Yeah.
days you missed? Cool. All right. See you later, Matt. Oh my gosh! No way! Oh, this is too nice. Yeah, a cutting board. Jeez, that's really actually too nice. Now I feel bad. Hey, thank you yesterday. I really appreciate that.
It was funny
Can you write that?
because so
Did she think it was you? Did you get caught like putting it there?
this is what happened. So the only thing she knows for a fact is that it's not me. So what happened is I had but she knows it's she doesn't know there's anyone in this office. But
She might.
so I saw your text like 2 hours after because I was in class. I taught 4th and 5th. And I had kids come for extra help right after, and she was like there the entire time. So it was like I had to leave. I had to head to tutoring. That's on my crowd. I'm like I have to get this to her. So she was kind of gonna have to know that it wasn't me. So she was fixated on her computer. I quickly grabbed the box, went down to the faculty room, stayed there a while. Cut the thing open, right? Cut it up and down there, and then
Which was a bitch
came-
to open, right?
It was a pain. And
Okay.
then fortunately she was on the phone with a friend, got off the phone, and then I said Sunita, the delivery from your Secret Santa, kind of almost giving you the impression that it was, because I walked up the stairs.
So
it was
it came
almost
from
like
downstairs.
it came
Dude,
from
you're the
downstairs,
best.
and then, so the only thing she knows for a fact is that it's not me.
Yeah, that's fine.
But it was really funny when she read it. She's like, oh, this is so funny, this class is about sake. And I'm like, no, it said 0, because it says for fuck's sake.
Yeah.
She thought it was about sake.
Oh,
Like
because
the
the word
wine.
sake. Sake
She
is
thought it was
spelled
a-
the
yeah.
same way as sake.
Or
Oh
several,
my
yeah, so she thought it was
God.
about sake, and I'm like, no, it says 0 fucks, or
Yeah, oh, for fuck's sake.
For fuck's sake. And she's like, oh, I don't get dirty. But she's like, oh, this is great. She's like, my daughter's gonna be drinking out of that glass and be like, oh, this glass great.
That's awesome.
So
All right.
is this it for today?
Thank you very much. Yeah, that's her gift for today.
Nice.
It's a little mini thing of prosecco. Oh, not
Oh,
this.
it's
No,
Prosecco?
sorry, not
Oh,
this.
okay.
What this is? It's a little prosecco with orange
Is this
juice in
your
it.
note?
Yeah.
That's so
With a
funny.
little thing of OJ in there, and then like the women like those face things.
Yeah,
with the
yeah.
face- So I said like for a Saturday morning or
Relaxing
something.
weekend
Yeah.
morning with or without the kids.
Meaning
Or
or prosecco.
or
we-
Prosecco.
It's with the kids. I don't know if you want the prosecco. You know. I like how they put the thing on here to show that this is like a cheese serving board. You know.
That's awesome.
Oh, this is so nice. Gosh. Wow. Jazz is gonna love this thing. Oh my god. We had an old cheese board, but it's kind of it's the end of its life, you know.
Uh-huh.
This is great. I'm glad I got Sunita this year. Not that I would have been pissed if I got someone else, but like it was just so much
Yeah,
easier.
you know more about
Oh.
her, yeah.
Dude,
so
every
it's
day
just-
I've had something planned, and
Yeah.
I gotta give her the. I did I tell you I got her a bullshit button. Did I tell you that one?
Did you? That's
You know, like
so
the that
funny.
was easy button kind of thing.
You have a bullshit.
It just says
button.
BS,
That's
and
so
it says in
funny.
like 10 different languages or
That's
tones,
great.
like bullshit. Yeah, I'm excited to give her that
That's
one.
great.